Now, when you're in the case with real distinct eigenvalues, there's something special that goes on. This is called dominance, and it's going to be a very, very useful thing to us later in our story. So let's take a little detour now and talk about dominance. Recall from the previous example we did where we had this matrix A that has columns 2, 3, and 5, 4. Now, we computed the eigenvalues, the eigenvectors. Lambda 1 was 7, and then the eigenvector for that v1 is 1, 1. Lambda 2 is -1, and v2 is 5, -3. Okay. In the case where we use that matrix to solve the system dx equals ax, so we're looking at continuous time, then what's the general solution? Well, x of t is a linear combination of the two eigenmodes. You have c1 times e to the 7t times the vector 1, 1, plus c2 times e to the -t times the second eigenvector, 5, -3. Okay, now let's think about this dynamically. What is happening to this solution as time evolves? Well, obviously, you got that e to the 7t, and it gets big. It goes to infinity, right? But let's think about it. That entire second term with the e to the -t in it, that's going to 0. So in the end, asymptotically, your solution is always approaching some constant times e to the 7t times this eigenvector 1, 1. Now, this is really interesting. This portion of the solution is what you might call a dominant eigenmode. Well, okay then. But what does that really mean? Well, let's assume that we are looking at a 2D linear system, and we're in the case where we have real distinct eigenvalues, lambda 1, lambda 2. Here's a definition. It's kind of a fake definition. We'll make it a little more precise in volume 3, but for now, here's our definition. Lambda 1 dominates lambda 2 if, in a continuous time system, lambda 1 is bigger than lambda 2. That's it. It's just the biggest eigenvalue. That's the dominant one. But in discrete time, we say that lambda 1 dominates lambda 2 if lambda 1 is bigger than lambda 2 in absolute value. And that distinction is important, and we're going to see why in just a minute. It is related to the stability criterion. Now, in this case, lambda 1 is called the dominant eigenvalue for the system. v1, the associated eigenvector, is called the dominant eigenvector for that system. Well, that's swell. But why do we have all this terminology? What's it for? It's for asymptotics. Here's the idea. If lambda 1 is the dominant eigenvalue, then your solutions x satisfy the following. In continuous time, the general solution, x of t, is c1 e to the lambda 1t times v1 plus c2 e to the lambda 2t times v2, right? Right. Okay, now watch this. Factor out an e to the lambda 1t, and what's left over? Well, in the first term, you have some constant, c1, times your eigenvector, v1. In the second term, you have c2, and then what? You have e to the lambda 2 minus lambda 1 times t times v2. Now, because lambda 1 is bigger than lambda 2, this is continuous time dominance. That means you have a negative exponent, and just as in that previous example, this entire second term goes to 0 as time goes to infinity. Your solution is asymptotically some constant times e to the lambda 1t times v1. Okay, that's continuous time. What about in discrete time? For a discrete time system, your general solution x of n is a constant c1 times lambda 1 to the n times v1 plus c2 lambda 2 to the n v2. Now here what we're going to do is factor out lambda 1 to the n. From the first term, that leaves c1 times v1. But from the second term, what do we have? We have c2 times quantity lambda 2 divided by lambda 1 all to the n times v2. Now, because lambda 1 is dominant, it's bigger than lambda 2 in absolute value, that means that that term in the parenthesis is less than 1 in absolute value. Taking higher and higher powers of that, that term goes to 0. And in the limit, as n goes to infinity, what do you have? You have everything asymptoting to C1, lambda 1 to the n, V1. Now, this might not seem like a big deal, but knowing something about the asymptotics of your solution can really be useful. Here's an example of using dominance in a problem from market systems. Let's say you have two companies, and company A has a customer base that's growing, and its natural growth rate is 7% increase year on year. Company B, on the other hand, has a slower natural growth rate. It's 4% every year. Now, if this were an uncoupled discrete time system, of course, company A wins. But we're going to add a little complexity here. The customers switch or defect. And every year, 2% of the customers leave company A and switch to company B. And 1% of the customers switch from company B's product to company A's product every year. Now, with this in place, what happens over time? It still seems like company A should win, but it's not entirely clear. So let's model this as a discrete time linear system. AN and BN are going to be the number of customers for company A, company B at time n. Our system is AN plus 1, BN plus 1 equals what? Well, AN plus 1 is going to be 1.07 times AN. That's that 7% increase. But then they lose 2% of their customers every year, minus 0.02 AN, but they gain 1% of company B's customers, plus 0.01 BN. Same thing for BN plus 1. It's 1.04 BN minus 0.01 BN plus 0.02 AN. If I collect all of these constants into a matrix, I get the entries are 1.05, 0.01, 0.02, and 1.03. I take that matrix, multiply it by AN, BN. That's my linear system. Okay, so what do we see about this matrix? Well, here are a few facts. I'm going to tell you that the eigenvalues are lambda 1 equals approximately 1.0573. And its associated eigenvector can be chosen to be 1.366 and 1. The second eigenvalue, lambda 2, is approximately 1.0227 with eigenvector v2 negative 0.366 and 1. Okay, we look at this, real distinct eigenvalues. Lambda 1 is the dominant eigenvalue, and this tells us everything. Why is that? Well, let's write out the solution for AN and BN, factoring out that lambda 1 to the n term just like we did before. The entire second term goes to 0 as n goes to infinity, and we're left with that first dominant term, which is a constant, times lambda 1, 1.0573, to the nth power, times the first eigenvector, 1.366 and 1. So as your time n goes to infinity, what do we conclude? We conclude, first of all, that both companies are growing at the exact same rate of about 5.73% per year. That's a bit of a surprise. Also, we can see exactly what the market share of customers is. It converges to fit the ratio of 1.366 to 1. That is, Company A has about 57.7% of the customer base, and Company B has the leftovers, about 42.3%. Both of these conclusions follow from dominance, and both are rather surprising.